All right, 1-5.
I brought it.
1-5 today. Let's see if there's anything. Yesterday we did the first one on the back of the Can We Predict Stock Values paper. Let's go back to that page. It's the back side of the stock values. And go down to number 3. A polynomial function has x-intercepts at 0 and 4. Okay, so we don't know what it looks like, but it has x-intercepts here, and your x-intercept, remember, are zeros, okay? So which of these must be true? Now, could it be a quadratic?
Yep.
Does it have to be a quadratic? No. So A could be true, but it doesn't, it's not a must true. G must change concavity on 0 to 4. Well, no, because if it looks like that, does that change concavity? No. G has an absolute maximum or minimum at x equals 2. Now remember, do we know it's quadratic?
No.
No. If it were quadratic, would C be true?
No.
Yes. If it were quadratic, C would be true. You would have either a high point at 2 or a low point at 2. Mrs. Ford, how do you know it's at 2? Because parabolas are symmetric. But I don't know that it's quadratic, so D says G has a relative max or min on the interval 0 to 4. Doesn't there have to be either a high point or a low point between here? I mean, even if the thing is crazy squiggly, since these two are connected, these 2 points have to be connected. Isn't there going to be either a high point here or a low point here, at least one? Yeah, so D is the true statement. All right, let's move on to 1.5.
Oh, SpongeBob. SpongeBob with the hat.
Given a polynomial function, if P of A is 0, then A is a 0 root. So these guys right here are called zeros, roots, x-intercepts, solutions. There's lots and lots and lots of different names for an x-intercept. If A is a real number, then if x equals A is a 0, then x minus A is a linear factor. You know this. You know this. If you have, I'll just stay quadratic. This means that x is 0 at 3, or y is 0 at 3 or 2, right? If these are x-intercepts, then those have to be the corresponding factors. You know that, right? That's easy. If a linear factor is repeated n times, the corresponding 0 has a multiplicity of n. So in other words, if I had this polynomial right here, that polynomial, I know my roots, my zeros, are x equals 3 and x equals 2. But this means that that factor happens twice. So we say this one has multiplicity 2, and this one has multiplicity 3. That's just vocabulary. Okay. Typically, we know that a graph of a passes through the zeros on the graph. So wherever the zeros are, the graph is going to pass through that. However, when a zero has a multiplicity greater than 1, the graph behaves differently. Do you remember this from last year? What happens when you have a squared factor?
Doesn't it squiggle?
No, it bounces. It bounces. It squiggles when you have an odd multiplicity. So if you have an even multiplicity, any even, it doesn't have to be 2, any even, when you get to that 0, in this case 3, you're going to bounce off of it. So if you're coming in from the top, you're going to bounce off and go back up. If you're coming in from the bottom, you're going to bounce off and go that way. If it has odd multiplicity, then it passes through, but it passes through with the same kind of wiggle that you get with a cubic polynomial. Okay? So a picture that has that going on means that root is at least 3 times.
So it would still look like a cubic, like the cubic shape from the 5%?
Yep. The bigger that odd number is, 5, 7, 9, the straighter, the less curvy the curve is, but they're still like squiggling. That's them. All right, the function is graphed to the right. Notice the behavior around the zeros. So do you see what happens at -1? See how it's squiggling down through that point? What's happening at 3? It's bouncing off. What's happening at -4?
Go straight through.
It's just going straight through. So if your factor only happens once, you go straight through. If it happens an even number of times, you bounce off. If it happens an odd number of times, you squiggle through. The graph of a polynomial will always be tangent to the x-axis at any 0 with even multiplicity. In other words, it's going to bounce off anytime you have an even number of those. Okay, complex roots. Some polynomials have roots that are imaginary. These guys are what we call real roots. They're actually graphable. They're on the x-axis. These are real roots. Sometimes you're going to have imaginary roots. You can count that before with your quadratics. That means you will not see them on the graph. So the graph is shown over here. To find the zeros, we set it equal to 0 and solve. So our imaginary roots are plus or minus I. Does that make sense to you? Right? What do you know? Solve that equation. Move the 1 over, take the square root of both sides. What do you get? Come on, Gus. This is all algebra 2. This is easy. All imaginary roots come in pairs. Come in pairs. You'll never get 2 plus I without 2 minus I. They gotta come together. If a plus bi is a root, then so is a minus bi. Those are called conjugate pairs. What is the conjugate of 4i? Remember, 4i is 0 plus 4i. So what would its conjugate be? Negative 4i. 0 minus 4, negative 4i. What is the conjugate for negative I?
Just I.
I. 2 minus 3i.
2 plus
2 plus 3i. And negative 4 plus 2i.
4
Negative
minus
4, negative 4 minus 2i. When we write the conjugate, only the I part changes. Okay? Now, what do you need to remember about that? Imaginary roots always come in pairs. Okay? You're going to need to remember that here in a minute. Alright, the graph of the polynomial function is shown above. So he's graphed some kind of equation. It is known that I root 3 is a 0. So we know that one of our roots is I root 3. Well, then what do we automatically know? Another one is gonna be negative I root 3. Because imaginaries always come in pairs. They come together with their conjugate. If f has degree n, what is the least possible value of n? Okay, so look at the picture. Look at the picture. What do you think the least possible value of n would be? We have another root at negative 1. Would you agree with that? What can you tell me about that one? Look at the curve. What's it doing?
Straight through.
At negative 1?
Bouncing.
It's bouncing. And if it's bouncing, then that means this guy has multiplicity of at least 2. And then you have another 0 at 3. What's happening at 3? It's going straight through, so that has a multiplicity of 1. So how many do we have? We have 1, 2, 3, 4, 5. So at the very least, that polynomial has a degree of 5. Because we have 5 roots, minimum 5 roots. How could there be more? Right here? Right? I don't know how many of these I have. I just know I have an even number. So I could have 4 of them. Or 6 of them. I don't know. Also, I could have more of these too. I don't know. So it's at least 5. At least 5. All right, consider the function above. We've already talked about the reminder. When we write f of x, we are referring to the y. Y bigger than 0 means the graph is above the x-axis. Y less than 0 means the graph is below the x-axis. Remember all those problems we did where you had to decide if the curve was positive or negative? Y positive, y negative, right? All right, look at the picture. Where does f of x equal 0? Negative 3, negative 1, and 3. So the answer to part A is the x values. So x equals, what do we say, negative 3, negative 1, and 3. That is the answer to A. Now what does B want to know? Where is the curve positive? So where is the curve positive?
Negative 3 to negative 1.
Between negative 3, so negative 3 to negative 1, a nice little open interval, right?
Or 3 to infinity.
Or 3 to infinity, yep. Perfect.
Isn't it? But there's no arrows on it.
You're right there.
Alright, my
I
bad.
think there's supposed to be, so I'm gonna pretend like there are. That's a cubic function. So cubic functions are gonna go in both forever and ever. You're right though. All right, where is the curve less than 0? Well, everywhere it's not greater than, so that would be negative infinity to negative 3. Or negative 1 to 3.
Brackets,
No brackets. Because brackets would mean that point was included. These are where we are 0. And did you notice in the problem, it says this? There's nowhere equal to on that? There's nowhere equal to on that?
Yeah. On C.
Oh, C does have brackets. So, oh, thank you, I didn't even notice that. So what would that be? This would have to be a bracket. And both of these would have to be brackets. Thank you. I didn't even notice that. Thank you. Yep, you're right. You okay? Now, we've already done this back in chapter P. We're going to do some more of it again. So we're looking at example 3 now, and we're going to walk through those steps he's got written above. So he says, step 1 is figure out where it equals 0. Well, that's easy. It equals 0 at 3, -1, and -4. Would you agree with that? That's where the polynomial equals 0. Now create a sign chart. Okay, we talked about that. So here's my number line. On my number line, I'm going to have -4, -1, and 3. Is that okay? Those dots will all be open. And now what am I going to do? Test values in each interval to see if they're positive or negative. So you pick a number over here, and we're showing our work. Remember how the whole time we were doing average rate of change, I kept saying, you gotta show this kind of thing right here. I kept saying you have to show that. Some of you didn't on your test, and you missed points because of that. You'll miss points on your AP exam if you don't follow the directions. This is always average rate of change. That's always there. Sign chart. Always pick a number in each interval. Even though I know there's a shortcut, you pick a number in every interval. So let's put in -5. -5 would give me negative, negative, negative. -5. Does that multiply to be positive? Nope, that's negative, don't want it. All right, -2. -2 would be negative, negative, positive. Does that multiply to give me what I want? Yep. So I'm going to color in that part of my graph. 0. Any number, I'll pick 0. Negative, positive, positive. That does not work. That gives me a negative. And 4 gives me positive, positive, positive. That does work, so I'll color that in. -4 to -1. 3 to infinity. Remember doing that in chapter B? Or review chapter? All right, go ahead. You and your partner do the next one. Be careful. This one's got a square in it. Pay attention to that. Did you get 2 consecutive intervals to work okay?
Do we want it?
two consecutive intervals to work. Well, think about this in terms of a graph. You know you're going to have a 0 at -2 and a 0 at 5, right? What's the degree of this polynomial? If you multiplied it all out, it would be x to the third. Cubic polynomials start down here. Think of your cubing function. Starts down here. But what does it do when it hits this point? It bounces and comes back down, and then it shoots up like that. And what are we looking for? We're looking for where it is less than 0. Well, where is it less than 0? Isn't it less than 0 all over here? So because of that bounce, you're going to have two, in this case, that are consecutive, both negative, but it could bounce this way and they would both be positive. So your every other rule that we observe in most problems doesn't work if you got a square, because that's going to bounce your picture. Is that what you got as your answer? Super. All right, equal width intervals are present, so it's good. We're going to examine successive differences. We did this yesterday, and when we did yesterday, remember we had to go all the way to the fourth difference before they matched. Let's see where these match. We're doing the differences. So, remember, the key is right here, guys. See how those are all the same size? That's perfect. So here, that is -1. This is 2. This is 5. And this is 8. These are called the terse differences right here. Do they match? No. So we are not linear. All right, let's go to the next differences. That is 3. Oh, they match. So we have a quadratic. Okay. All right, you go ahead and do B. See what you can come up with for B. Again, the inputs, the x's, are evenly spaced. That is crucial. Differences, second differences, third difference, so this is a cube. Now I want to verify that on your calculator, so let's go to stat, edit. So we're going to put these points in as L1 and L2. Here's L1, so go to stat edit, and we're putting in L1, and then we'll go to L2. So now the points are in. Anybody remember how we get an equation out? I want you to see with your own eyes that this is going to be a cubic equation. want you to see that. Does anybody? No. Right now, certainly we could plot those points and kind of look at them. Does it make a cube shape? But we go back to stat, calc, and then down to cubic regression. And the calculator always tells you with whatever regression, it tells you what the format of your equation will be. And this will be a cubic descending order. And then it gives you values for A, and B, and C, and D. Does anybody's calculator have, after it goes down A, B, C, D, gives you those numbers, does anybody's calculator have anything else in that list? You guys with the old calculators, like mine, the fat ones, should have something else popping up. What else is popping up? Anything?
Mine just says nothing.
Alright, you gotta figure out how to get it in there. I know there's a way, I just can't remember. That'll be my project tonight. I'll figure out how to get it. But mine, I have told it to give me this, and down at the bottom of all the A's, B's, and C's, it says R squared equals 1. And one of the things we're going to learn in this in this unit, I think it's in this unit, is that that number is really, really important. The closer that number is to 1, the more accurate my equation is. So when it is 1, what does that tell me? I have a perfect fit. So you figured out that this thing was cubic, and we let the calculator do the work, and it verified that that's cubic. All right? Try this. Go back to stat, calc, and pick quadratic regression. Now, does it give you numbers? Yes, it will always give you numbers. But the R value is less than 1. So what does that mean? The cubic is a better fit, right? Well, you already figured that out arithmetically, right?
Where do you see the R value?
Well, I'm gonna have, if it's not showing up, I gotta figure out how to get it. I can't remember. I'll have to tell you how to get it. That'll be my project tonight. Or you can Google it and get it too. But my point was, I wanted you to see that this deal here, where you start doing all these differences, that actually is, I mean, it's true. I think it's one of the most amazing things. That whenever the differences start matching up, that's the degree of your polynomial. I can tell you're all confused by it too. All right, let's turn the page and talk about even and odd. I can't remember, did we talk about this in chapter P? No? All right, so let's get our vocabulary down. Even means you're symmetric over the y-axis. Means you have y-axis symmetry. So if you look at the picture that he drew, do you see the symmetry across the y-axis? And what it means is that if you plug in a negative number, or if you plug in the corresponding positive number, it doesn't matter. So if you look at your picture, what's f of negative 2? F of negative 2? Negative 3. What's f of positive 2? Negative 3. So what it means to be even is the sign on x doesn't matter. The sign on x doesn't matter. That's what it means to be even. odd means you have symmetry over the origin. Odd origin. And that test says if you put in a negative, you will get out a negative. So look at the difference here, kids. What does this say? If you put in a negative, it doesn't matter. Over here, if you put in a negative input, it changes the sign of your output. And that makes sense. Look at the picture. What do you get if you put in 1? Put in 1, you get about -1.5. What do you get if you put in -1? +1.5. So changing the sign on the ins changes the sign on the outs. That is your test for symmetry about the origin. Okay, so now with that in mind, you are going to determine if this guy is even, odd, or neither. So all you gotta think about is, what happens if I put in a negative x? Is anything gonna change if I put in a negative x? Think about it. What happens when you take a negative to the 4th power?
Positive.
How about a negative to the 2nd power?
Still positive.
Did anything change when I put in a negative x? Therefore, this function is even. Does that make sense to you? Is your hand up?
Yeah, so it doesn't just have to do with the degree?
No, it doesn't. Because if I change this, maybe put an x +2 or something here, then it would no longer be even. Even though it has an even degree, it would no longer be an even function. Certainly that plays into it, no question about it, but it's not enough to just look at the degree. All right, try B. Even, odd, or neither. Those are your choices. And all you have to do is plug in a negative x and see what happens. What's negative x cubed? Negative x cubed? Minus 3x minus 1. Now, is that the same as the original? Here was the original. Is that the same? So clearly it's not even. Is this the opposite of the original?
No.
Nope. Therefore, it's not odd. So here's an example of one where you might think it's odd, but it's not. Because when I put in negative x, I should have gotten negative, negative, positive, and I didn't. So it's not odd. It's even. What do you think about C? You think that's even or odd or neither? Looks odd to me, but here's how you can check. What do you get if you put in +1? -3. What do you get if you put in -1? +3. So changing the sign on the in, change the sign on the out, that makes it odd. Pictures are easier to tell, but if you need a way to test it, just pick a point. All right, what do you think about D? That's a neither. Does it have symmetry?
Yep.
Yes, about the line x equals 1, but that doesn't make it even or off. All right, let's look at the back side of what's up with the zeros. Let's look at the back side of that. Take a minute and see if you can answer question number 1. Check your understanding. It's got a picture of a 6-degree polynomial. See if you can answer that. Every time you touch the x-axis, you have a 0.
Why it's right here? So they like, I made it
What were your zeros? Where did you come up with the zeros? X equals
Negative
Yeah.
3
Negative
multiplied
three.
with
2 and 4.
not one.
And negative 3 had a multiplicity of 2. 2 has a multiplicity of 3. And 4 is what we call a simple 0. It only happens once because the curve goes straight through. What do those add up to? 6. This is a 6th-degree polynomial. Are there any imaginary roots? No, because a 6th-degree polynomial has 6 roots. That's the fundamental theorem of algebra. So, no imaginaries. We're all good. Number 2, a polynomial has zeros of 4, and that has multiplicity 2, negative 2, and 3i. What is the minimum degree of the polynomial? Minimum degree of the polynomial. 5. How do we know it's 5?
It's always conjugate for 5.
Because that's 2, that's a third, and these guys come together, so that makes 4 and 5. Remember, anytime you have an I, you don't have 1, you have 2. Write an equation for this polynomial in factored form. What would this factor look like? X minus 4 squared, beautiful. What would this one look like? X plus 2, just X plus 2. What would this look like? X minus 3i and X plus 3i. When you went from the 0 to the factor, what you really did was subtract this from both sides, so you have x minus 4 equals 0. That's what you really did. So does it make sense then that this one would be x minus 3i? And that one is x plus 3i? These are called the linear factors because each factor is a plane x. And normally, when we break it all the way down, we want the linear factors, which is exactly what we have.
Could you also write it as x squared plus 9?
But then it wouldn't be linear factors, then that would be a quadratic factor. And it doesn't stipulate in this problem, but it does in the next one. So yes, absolutely, that multiplies together to give you x squared plus 9. But usually factored form means linear factors. All right, 3a, find all the zeros. All right, what's one of them right off the bat? -6. How are we gonna get the other ones?
Quadratic formula.
Probably use the quadratic formula, so -2 plus, we could also complete the square, if you like that better, because it's easy in this problem to complete the square. B squared minus 4ac over 2. Okay, it's gonna be imaginary. What's it gonna be? Is it 4 on? Did I make a mistake? Is that right? What do you mean? Are these are okay then for the roots, or the zeros, same thing? Okay, now write the equation in fully factored form. So what will the factors be? There's going to be 3 of them because there are 3 answers there. What are those factors going to be? X plus 6, absolutely. X plus 1 minus 2i, yes indeed. And x plus 1 plus 2i. Nobody had a problem moving this over and making it x plus 6, right? So when I move these over, it's going to be x plus 1 minus 2i and x plus 1 plus 2i. What should happen if you foiled that? That would be a giant foil. What would happen if you foiled that? What should you get, Alex?
X squared plus 2x plus 5.
Exactly. This is the quadratic factor that we started with. These are the linear factors. Perfect. All right, let's go to the back of the next page where it talks about even odd functions. See if you can sketch the other half of this odd function. It's odd. Odd, 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 odd. See if you can sketch the other half of the odd function. Remember what it means to be odd. Sketch the other half of it. you got it, bring it on up and draw your picture and we'll talk about it. Remember, it's odd. It would be a whole different conversation if it were even. This one's odd.
Where's your brush?
Look at my suit that I picked Jordan.
Black hole from Interstellar.
Better than me.
Black hole from Interstellar.
It's supposed to be a 2, not 3. It's supposed to be a Y level. It's supposed to be a Y level 2, not 3. Y level 2.
Don't.
So you got it wrong. You wrong on the test.
You fail. You fail.
What do you think? Now, Declan, did you just kind of eyeball it when you did that, or did you actually have some math behind what you did? I think you're right. But what was your approach to it?
Well, I guess I kind of had one at first that checks like the points. The points are like they're starting to flip.
Yeah, so when we talk about checking it with the points, remember, what does it mean beyond? It means if you change the sign on in, you're gonna change the sign on out. So if you start, let's just start with this point right here. If I change the sign and make this -3, then I should get the opposite of 0, which is still 0, right? If I change the sign, make this a -7, then I need to get a +2. I can't change the sign on 0, but if I do -0, I have to get -3. So if he just reverses the signs of the points he's got up here and connects the dots, he's gonna have a shape. Alex?
Can it be a function though, because it's a 0 at 2 places? This is at y equals 0 at 2 places. Like that failed the vertical line test.
Oh, I
Does
see
one of
what
them
you
have to
mean
be an
right
open
here.
circle?
We'd have to have one of those be open.
I can include that too.
Did you? Yeah. That would not be a function, because we currently have 2 points there, but we have to make one of them open. Because it wouldn't be a function otherwise, you're right. You're right. Now, when I thought maybe he eyeballed it, because if you're symmetric about the origin, doesn't that mean that positive is gonna become negative? So all of these points are positive, and all of these are negative. And then similarly, what are these? These points are positive, so they're gonna become negative, positive. So quadrant 1 gets mapped in quadrant 3, and 4 gets mapped in 2. So that would be another way to think about it if you didn't want to use the points. Beautiful. All right, number 2. If 3, -18 is on the graph of an even function, what other point is guaranteed to be on the graph? -3, -18. Because if you're even, okay, what does that mean? Change the sign on in, and it does not impact out. So -3, -18, perfect. What if it were odd?
-3 positive.
-3 +18. Yep. All right, hurry up quickly. Number 3, even, odd, or neither. Prove your answer algebraically. What does our algebraic proof look like? it mean to be even? Change the sign on
Y,
in, and nothing happens to out. Alright, so let's change the sign on the inputs here. So negative x to the fifth, negative x to the third, plus 3. Is that gonna impact my answer, or am I gonna end up with the same answer? It's gonna change my answer, isn't it? Is that gonna become negative y? Watch it, that's an either. That's an either.
So if you had a coefficient, it's always gonna be like. Right, you got like
Nope,
you got like a number.
nope, not true. Okay? This is not odd, because if it were odd, you change the sign on y, that would make the 3 negative.
So can it not be odd if it's,
But, yeah, when we got so much to memorize, I wouldn't waste my time with that. All right, not even or odd, not even or odd for that one. And finally, true or false? If the statement is true, explain, okay, if it's false, okay. All even functions go through the origin. Does every even function in the whole wide world go through the origin?
No.
Can you think of one that doesn't?
X squared plus 1.
X squared plus 1, beautiful example. Is this an even function? It sure is, and it does not go through the origin. If each term of a polynomial function has an even exponent, the function is even. So it would be something like 6x to the 4th minus 3x squared plus 5, something like that. Or 10x to the 8th plus 4x to the 6th. As long as each term has an even exponent, would you say it's going to be even?
What about the no? Because of the 5.
What?
I would say no, because the 5 might not change. Or like
Well, but here's the point, if it's even, nothing's going to change. So if you put a negative in here, will that term change? And that term won't change? And that one won't change, which is a good thing. That means I'm going to get the same answer. So yeah, I think that's a true statement. I think that's a true statement. All right, so 1.5 is now due on Thursday.